Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain the dimensional changes for a thin cylinder when it is subjected to internal fluid pressure. The internal fluid pressure induces longitudinal, circumferential and volumetric strains in the cylinder, and as a result of these strains the dimensions of the cylinder will change. In today's class I'll explain how to find out these dimensional changes for a thin cylinder. In the earlier class we obtained the expressions for longitudinal stress and circumferential stress induced on a cylinder walls. These circumferential stress which are acting along the circumference is inducing a stretching on the cylinder walls in the circumferential direction. This stretching will increase the circumference since it is a tensile stress that will try to increase the circumference of the cylinder. As a result of this increasing circumference, the diameter changes. Now the longitudinal stress in turn is trying to increase the length of the cylinder. So this increase in length and circumference are direct strains. It also induces strains in the lateral dimension. Each stress is inducing strains in the lateral dimension. For example, direct strain induced by sigma c is to increase the circumference of the cylinder. It also tries to reduce the length of the cylinder. So that is a lateral effect. And sigma L, it is trying to increase the length, and at the same time its lateral effect is to decrease the circumference. Now let us see what is the circumferential strain. Circumferential strain is change in circumference divided by original circumference. So what changes for the circumference is taking place as a result of this stress divided by original circumference will give the circumferential strain. Circumferential change is caused due to the changes in diameter. So circumferential strain is caused by the changes in diameter of the cylinder. Now we will calculate the circumferential strain. Now let the initial diameter of the cylinder is d. Okay, initial diameter is d, and as a result of this stretching on the walls, okay, the stresses are acting and the walls are getting stretched and the diameter increases, and let us take the final diameter as d plus delta d. Now you can calculate the initial circumference and final circumference. Initial diameter is d, so initial circumference is pi d. Okay, the circumference is pi d, and after stretching this diameter increases to d plus delta d. So the circumference has increased, and since the diameter is d plus delta d, final circumference is pi into d plus delta d. So final circumference is pi into d plus delta d, and initial circumference is pi d. So pi into d plus delta d minus pi d divided by initial circumference is pi d, which will give the circumferential strain. So if you expand this, pi d minus pi d, that cancels, pi into delta d divided by pi d. So pi cancels, you get delta d by d, and delta d is change in diameter and divided by initial diameter, so that is equal to strain in diameter. So delta d by d is strain in diameter. So finally we can see that circumferential strain and strain in diameter are one and the same. So whatever circumferential strain is equal to the strain in diameter. Okay. Now the stresses are acting like this. Sigma c is hoop stress or circumferential stress is acting like this. Sigma L is acting along the longitudinal direction. Now these stresses, I just put sigma L along x-axis and this sigma c along y-axis. Okay, So this element I have shown here, but I have straightened it and shown. Okay. So sigma L along the length, okay, length, this is a length, this is x-axis. Okay. So I have taken along the length sigma L, perpendicular direction, this is perpendicular direction you have sigma C, that is circumferential stress. Now you have already studied generalized Hooke's law. We know the strain in x direction is, that is Ex, is sigma x by E minus nu sigma y by E minus nu sigma z by E. But sigma z is not there, so it reduces to two terms. That reduces to sigma x by E minus nu sigma y by E. So that is a general equation. Now here sigma x is sigma L and sigma y is sigma C. So you can write, instead of Ex is sigma x by E minus nu sigma y by E, you can write it as EL, x direction, it's along the length, and sigma x is sigma L and sigma y is sigma C. So I just replace sigma x and sigma y by sigma L and sigma C. So you get strain in length as sigma L by E minus nu sigma C by E. So this stretching in this direction is inducing a direct strain which is sigma L by E. And also in x direction, due to this stress, there is a lateral strain in this direction. So sigma C stress is inducing a lateral effect on the x direction or longitudinal direction. So that effect is minus nu sigma C by E. Okay. So it's a direct strain due to loading or stress in longitudinal direction, and this is a lateral effect of circumferential stress in the longitudinal direction. Now you know sigma L as PD by 40 and sigma C as PD by 2T, and we can substitute and take PD by 40 outside. You get PD by 40 into PD by 40. If you take outside, you have to multiply numerator by 2, so you get 1 minus 2 nu. So this is a longitudinal strain. So you remember this formula. EL is longitudinal strain is sigma L by E minus nu sigma C by E. Already proved that circumferential strain and diameter strain are one and the same. Okay, so EC, circumferential strain, is equal to strain in diameter, and EC along the circumferential direction you can find out the strain, that is EY you calculate. No, EY is sigma y by E minus nu sigma x by E. So instead of y direction you have circumferential direction, so I just put it EC, okay, which is also equal to ED. It's equal to sigma C by E, that is sigma y is sigma C here, sigma C by E minus, instead of sigma x we have sigma L minus nu sigma L by E. So sigma C is PD by 2T, sigma L is PD by 40. So PD by 2T minus nu PD by 40, or if you take PD by 40 outside, PD by 40 into 2 minus nu. So this is circumferential strain, and you can remember circumferential strain as EC, that is a direct, in a circumferential direction, direct strain sigma C by E minus other stress is producing lateral effect, so minus nu sigma L by E. Here longitudinal direction you have direct strain due to stress in longitudinal direction, so whatever subscript is EL sigma L by E, the other stress is producing lateral effect, so minus nu sigma C by E. So this is a longitudinal strain and circumferential strain or diameter strain. So once you know this longitudinal strain and diameter strain, you can find out the changes in dimensions of the cylinder. Also you can calculate the volumetric strain. Volumetric strain you have already studied for a cylinder. The volumetric strain is given by EL plus 2 ED. EL plus 2 ED. So we are taking in the fluid inside. The fluid inside is in the cylindrical shape, and as the length increases, the fluid length, the length of fluid contained inside is increasing, and the diameter is also increasing. The fluid inside the cylinder, the diameter will increase and the length will increase. So the inside contents, that is fluid, is in the form of a cylinder, and this cylinder dimensions will change. Okay, the diameter is increasing and length is increasing. So there is a strain in length and strain in diameter. So these strains will induce a volumetric strain. So volume will change, and you can say volumetric strain is EV is EL plus 2ED. So this we have studied earlier. Volumetric strain is for any object, the volumetric strain is Ex plus Ey plus Ez. So here in the x direction you have length, y direction you have diameter, z direction you have diameter. So EL plus ED plus ED or EL plus 2ED. Now you can remember this equation. Easiest way to calculate the volumetric strain, find out longitudinal strain, here longitudinal strain and circumferential strain or diameter strain you find out. Then you can add those longitudinal strain plus 2 times diameter strain will give the volumetric strain. Once you know the volumetric strain, you can calculate the volume change in the cylinder. Now if you want to reduce this into in terms of pressure and other cylinder properties, you can write it as EL. We already know the strain in length as sigma L by E minus nu sigma C by E, and strain in diameter or circumferential strain is sigma C by E minus nu sigma L by E. And already we know sigma L is PD by 4T, sigma C is PD by 2T. Okay, sigma C PD by 2T and sigma L 4 PD by 4T is substituted. Now you have PD by 4TE plus here 2 PD by 2TE. So if you take 2 inside, PD by TE, okay, PD by TE, so this term. Now minus nu PD by 2TE and minus this is 2 by 4, it is PD by 2TE. So minus PD by 2TE, here also you will have minus nu PD by 2TE. That is these two terms if you sum up, you will get minus nu PD by TE, because half and half it will make 1. So this is half of nu PD by TE and this is also half of nu PD by TE. So that will make it 1 minus nu PD by TE. Now if you join this together, you get PD plus 4PD, that is 5PD divided by 4TE. So this if you combine, you get 5PD by 4TE minus nu PD by TE, or PD by TE you can take outside, 5 by 4 minus nu, or PD by 4TE, 4 is taken outside, PD by 4TE into 5 minus 4 nu. So this is the volumetric strain in terms of pressure and the cylinder properties. Now to find out the volume change, so this is a volumetric strain, you can multiply volumetric strain with the initial volume of the cylinder. So volumetric strain is PD by 4T into 5 minus 4 nu into initial volume is pi by 4 d square L. The volume of the fluid inside is pi by 4 d square into L. So you will get the volumetric change in volume as pi PD cube, pi PD cube L divided by 4 into 4, 16 TE into 5 minus 4 nu. So this can be remembered as a formula for change in volume of a thin cylinder when subjected to pressure, fluid pressure P. Pi PD cube L divided by 16 TE into 5 minus 4 nu. So this formula, if you know, directly you can apply and find out the change in volume. Even otherwise you can calculate the change in volume. You need to calculate EL, as EL is sigma L by E minus nu sigma C by E, and ED you can calculate sigma C by E minus nu sigma L by E Then you find out EV. After getting EV, just multiply with the initial volume, which will give the change in volume of the cylinder. And let us work out a numerical example. A thin cylinder, 300 mm internal diameter, 1 meter long and 12 mm thick, is subjected to internal fluid pressure of 5 megapascal. Find the change in length, diameter and volume of the cylinder. Take nu is equal to 0.25 and Young's modulus E is equal to 200 gigapascal. So it's a thin cylinder which has got internal diameter 300 mm and the length is 1 meter and the cylinder walls are 12 mm thick and it is subjected to internal fluid pressure 5 megapascal. So you have to find out the change in length, diameter and volume of the cylinder as a result of this internal fluid pressure 5 megapascal. The Poisson's ratio is given and the Young's modulus of material is given. So you can find out the circumferential stress sigma C as PD by 2T. Okay, pressure is 5, diameter is 300 and the thickness is 12 mm. So PD by 2T will give the circumferential stress as 62.5. So once you get the circumferential stress, half of that is Hooke stress 31.25, or you can use PD by 40 formula, get the longitudinal stress as 31.25. Now you can find out the diameter strain. Okay, diameter strain is or EC, this is EC, circumferential strain or diameter strain are same. So ED is equal to sigma C by E minus nu sigma L by E, and it's 1 E can be taken outside, 1 by E into sigma C minus nu sigma L, and E is Young's modulus is 200 gigapascal or 200 into 10 raised to 3 Newton per mm square. Sigma C we got circumferential stress 62.5 and sigma L is longitudinal stress 31.25. Poisson's ratio is given 0.25. So which will give the diameter strain as 0.00027344. So this is a diameter strain, it has no unit. Now this is the change in diameter per unit length. So if you multiply with the diameter of with the strain, you will get the change in diameter. So change in diameter delta D is ED into D. ED is delta D by D. So delta D is ED into D. So strain, this is a change in length in unit length. So in 300 mm length, you multiply with the 300, which will give the change in diameter as 0.082. So you are multiplying the diameter strain with the diameter, which will give the change in diameter as 0.082 mm. Now longitudinal strain EL is sigma L by E minus nu sigma C by E, or 1 by E into sigma L minus nu sigma C, or E is 200 into 10 raised to 3, sigma L we know longitudinal stress 31.25 and sigma C circumferential stress is 62.5 and nu is 0.25. So which will give the longitudinal strain as 0.00007813. So this is a change in length in unit length of the cylinder. So to find out the total change in length, you have to multiply the strain in length with the initial length of the cylinder. So this is 7.813 into 10 raised to minus 5. Okay, I just move 5 decimal places here, 2, 4, 5 decimal places. So you get 7.813 into 10 raised to minus 5 into length is 1 meter or 1000 mm. So I multiply with the length of the cylinder, which is 1000 mm. So you get the change in length as 0.07813 mm. So this is a plus you are getting, that means increasing length, and even the diameter has increased. So the dimensions of the cylinder has changed, diameter has increased, length has increased. Initial length was 1000 mm, now it is 1000.07813 mm. So it has increased from 1000 to 1000.07813 mm. Even the diameter has increased. Now this will induce a volume change. Volumetric strain EV is equal to EL plus 2ED. So strain in length we got 7.813 into 10 raised to minus 5 plus 2 times diameter strain is 2.7344 into 10 raised to minus 4. So substituting EL and ED, you will get the volumetric strain as 0.0006251. So this is a volumetric strain or change in volume in unit volume. So it has no unit. Now to find out the change in volume, you can multiply this volumetric strain with the initial volume of the cylinder. So EV this into pi by 4 d square L. So cylinder volume is pi by 4 d square is area of cross section into length. That will give the initial volume. So EV is 0.0062501. Okay, EV I have substituted into pi by 4, diameter is 300 mm and length is 1000 mm. So substituting this, you get change in volume as 44,179.354 mm cube. This is in mm cube. If you have to convert into meter cube, you have to multiply with 10 raised to minus 9, or centimeter cube. If you want to convert, you just multiply with 10 raised to minus 3. 10 raised to minus 3 means 44.179 centimeter cube. Okay, meter cube will get a very small quantity, so it's in mm cube. So the change in volume is 44,179.354 mm cube. So we got the change in length, change in diameter and change in volume of the cylinder as a result of the internal fluid pressure acting on it. That's all for today. Thank you for watching.